We'll see if this works. Okay. Record. Okay. Well, we'll see where the video picks up. So we don't know what the population standard deviation is. Our standard deviation sigma is unknown. So what we're going to do is we're going to use the sample standard deviation. Okay? We're going to say, all right, I don't know the standard deviation of my population, but what seems to be a reasonable guess would be the standard deviation of my sample, right? So I have a sample, and I'm going to use the standard deviation of my sample as kind of a guess for what the standard deviation of the population is, right? And that sounds like a reasonable thing to do, and it is. And so we're going to estimate the standard error using S divided by the square root of n. So instead of the population standard deviation sigma, we're going to just take the standard deviation of my sample. So that seems like a reasonable thing, and it is a reasonable thing. The only issue is that it brings in additional uncertainty. Now we're not sure if kind of the standard error that I'm using, I'm estimating it. Is it too big? Is it too small? There's additional uncertainty, right? So what we'll do is, so one issue is that if your standard deviation S is too small, it's problematic because the resulting confidence interval could end up being too narrow. And if your resulting confidence interval is too narrow, you could end up making the wrong conclusion, right? Because we look at, if a value falls outside of the confidence interval, we're going to say, I've got evidence that it's not going to be this value. I feel confident that it's not any of these values outside of the interval. So if you end up with an interval that's too narrow, you're going to be kind of rejecting or throwing away too many values. So to kind of compensate for this, so we don't end up with an interval that's too narrow, we're going to just kind of like fudge the numbers and just build in a little bit of buffer. So if we knew the population standard deviation, we'd say let's go up or down 2 standard errors or 1.96 standard errors. Okay, if we knew the population standard deviation, we would do that. And now we're going to just say, you know what, let's build in a little bit of buffer. And instead of going up 1.96, let's just go up a little bit more, 2.1, okay? And we'll just kind of build in a little extra cushion to just play it safe. That's kind of the idea here, okay? So we don't want to end up with an interval that's too narrow, so you know what, let's just throw in a little extra, okay? It's kind of just like, I don't know, like how much food should you order for the party, right? And you might say, well, you know what? I don't know exactly how many people are going to come. I don't know exactly how many people are going to eat, how much people are going to eat. So, let's just order a little bit of extra so we don't run out, okay? Because we don't want to run out. So we're going to just kind of make our interval a little bit wider, right? And we're just kind of finagling, just fudging the numbers, okay? Now, how much do I need to kind of inflate our numbers by, okay? That's going to come from something called the t-distribution, okay? T-distribution looks a lot like the normal distribution, but it's wider, has thicker tails. And our sample size plays a role in what we use, okay? And this kind of makes sense in that if you have a very big sample, like let's say you surveyed like 600 people, then you could expect the standard deviation of your sample, that's huge, to be very similar to the standard deviation of the population, right? You've got a big sample, so whatever estimate you get from your sample is probably going to be a pretty good estimate for the population standard deviation, okay? So instead of using 1.96, maybe you just inflate the number a tiny bit, use 1.99. Okay. On the other hand, if your sample size is really small. Like you have a sample size of, say, 8 people or 10 people, okay? Now you're trying to estimate the standard deviation of the population based on this little sample. You might be wildly off, okay? And so you factor this in, and instead of using 1.96, you inflate your number a lot more. Maybe you use something like 2.36, okay? A number that's a lot bigger, right? And this all kinds of comes into, is accounted for in something we call the degrees of freedom, okay? The degrees of freedom is our sample size n minus 1, at least for this confidence interval, depending. In other courses and in other situations, you might have a different formula for the degrees of freedom. But for this confidence interval, our degrees of freedom is our sample size, n minus 1. And I don't feel like getting into the concept of degrees of freedom too much, so we'll just ignore it, okay? But one thing to note is that as your degrees of freedom approaches infinity, then basically we're saying we're taking bigger and bigger and bigger and bigger samples that approach infinity in size. And in that case, your t distribution will end up matching the z distribution, and will end up matching the normal distribution. And you would not need to do any kind of compensation, and you would just use 1.96 for a 95% confidence interval. Okay. Interesting story about the t distribution is that it was kind of discovered or created by William Gossett, an employee of Guinness Brewery from Ireland, and he was kind of like this quality control engineer, and you can watch these videos about it. The t distribution is part of your reference tables, so you have your reference tables with a normal distribution, and here we have reference tables with the t distribution, and this is what it looks like, okay? And so across the top you have the confidence level, and we can see 95%, and then on the left hand side it says degrees of freedom, and you can see when you reach infinity degrees of freedom, for 95% confidence we use the number 1.96, okay? And then for anything less than infinity degrees of freedom, we use a slightly bigger number than 1.96, right? We adjust the number to 1.984, to 1.99, and so on and so forth. And as our sample size gets smaller, degrees of freedom 8, degrees of freedom 5, degrees of freedom 2, okay, the amount we need to compensate gets much, much bigger, and we're using, very big numbers here. All right, so we put this all together and we create the confidence interval formula, and we have x bar plus or minus t star, or critical value t, times s divided by the square root of n. And so here's a silly example. I have a dog, and he's a Shiba Inu, and so he has so much fur, and he sheds a lot of fur. And the other day I was just kind of like brushing him and gathering up his hairs, and I was just like, I wonder what. So anyway, this is a silly example. Okay, but anyway, let's say we took 10 random hairs from the dog, and we decided to measure how long each of these hairs are. And we'll say the average length, the mean length is 4.2 centimeters, and there's a standard deviation of 0.2 centimeters. So some hairs are a little bit longer, some hairs are a little bit shorter, but on average the length is 4.2, standard deviation of 0.2. So we'll make a 95% confidence interval. And you know what? We'll just show you the numbers here, okay? So we go to our reference table, our t distribution table, and we have 9 degrees of freedom, right? We have, our sample size is 10, so 10 minus 1, I have 9 degrees of freedom. So I'm going to go to 95% confidence, 9 degrees of freedom, and the number in my table is 2.262. So I'm going to plug that in. I plug in all the other numbers from my problem. My average is 4.2. My standard deviation is 0.2. My sample size is 10, so I divide by the square root of 10 here. And so my confidence interval ends up being 4.2 plus or minus. This whole thing over here multiplies to 0.143. And so my resulting confidence interval is 4.057 to 4.343. So I say I'm 95% confident that the mean length of all the hairs on my dog is somewhere between 4.057 and 4.343 centimeters. All right, so what kind of conclusions can I make? What kind of statements can I make based on this? So let's talk about the interpretations. We would say I'm 95% confident that the mean length of all hairs on the dog is somewhere between 4.057 and 4.343 centimeters. So these next few statements, we've seen them before, but when we were talking about confidence intervals for proportions. And now it's the same kind of logic, but they apply to the mean of a population. So do we have evidence that the mean length for the entire dog, for the entire population of all hairs, is different from 4 centimeters? Okay, well, we ask, is 4 inside my interval? And it is just outside of the interval, right? The interval starts at a number a little bit above 4.0 and ends at a number 4.343. So I'm 95% confident that whatever the number is, it's between 4.05 and 4.343. So could it be 4.0? I'm going to say I'm pretty confident that it's not. Now, it could be, and I would be surprised if it were, but I'm going to say I'm pretty confident that it's not. I would say I have evidence that it's not going to be 4.0. It's outside the 4.0 is outside the range. It's not a plausible value. Okay, do we have evidence that the mean is different from 4.1? Okay, now 4.1 is inside the interval, so the number could be 4.1. It's not guaranteed that it is 4.1, but it could be 4.1. So it's a plausible value. I can't say that it's different from 4.1. It could be 4.1. But on the other hand, can I say it's equal to 4.1 or equal to 4.2? And the answer there is no, I can't say that either, right? So I can say, well, it could be 4.1, but I can't say that it is for sure 4.1. I can't say that it's for sure 4.2 either, right? So 4.2 is kind of smack in the middle of my confidence interval, but we can't say that it's certainly equal to 4.2. All we can say is 4.2 is a reasonable value. It's plausible. And that's what we have there. Okay. Here is our hypothesis test. Now we'll do a hypothesis test, okay? I kind of went over the interpretations for the confidence interval rather quickly, but I feel like we're okay with it because we've seen it with proportions. So, okay, moving on, we'll do hypothesis tests for mu. And again, we might go through this, relatively quickly, but there are some key differences, all right? So it's very similar to doing hypothesis tests for proportion, but now we're dealing with a mean. And, the only kind of key difference is the way you calculate your standard error is different. And then instead of using the Z table, we're going to use the T table. And how we use the T table is also quite different. So we'll take a look at that. Your second view quiz answer for today is the letter E. E as in elephant. E. All right, so we'll just work through an example. And we're going to ask, is the average weight of an apple 5 ounces? Okay, so like you go to the grocery store, they sell apples. Is the average weight of an apple 5 ounces? Okay, I don't know. I'm just making up some numbers here. Okay, So let's say you get a random sample of 20 apples, and you decide to measure the weights of these apples. Okay, and after you measure the weights of these apples, the mean weight is 4.5 ounces and a standard deviation of 0.7 ounces. And so now we ask, does our data provide evidence that the average weight of an apple is not 5 ounces, right? So I'm asking, is the average weight 5? And when I take a random sample, my sample average is 4.5, okay? So the fact that I got 4.5, is that evidence that the mean weight of all apples is not 5 ounces? Okay, so again, I'm just making up numbers. I have no idea. So to set up our hypotheses, we're going to write hypotheses about the population. Okay, so we're going to, when we write our hypotheses, all right, so we're going to say the mean weight, mu, is equal to 5. Okay, so we're talking about the mean. So for proportion, for here we're talking about the mean weight of apples. So our null hypothesis is that mu is equal to 5. And based on the way our question is phrased, we're asking, do we have evidence that the average weight is not 5 ounces? Okay, so our alternative here is going to be two-sided, and it's just going to be that mu is not equal to 5. Okay, don't use x bar and don't use p, right? So p is for proportions, mu is for the mean, x bar is for samples, mu is for the population. Okay, if we want to use words, we could write the average weight is 5 ounces versus the average weight is not 5 ounces. All right, we'll have to choose a significance level. Let's just use alpha equal to 5%. That's kind of a safe number. And then we'll also check conditions to use the central limit theorem. Okay, so central limit theorem, it said we selected a random sample of 20 apples. And again, I don't know if this is actually possible. How do you get a truly random sample of 20 apples? I don't know, but we're gonna just, maybe our population will just be all the apples at the grocery store or something. But we select some a random sample. The large sample condition, this may or may not be met. Okay, we said rule of thumb 25 or bigger is going to be good enough for most cases. Here we're at 20, so we're on the larger side of a sample, but it could be not big enough. Usually, if your data is unimodal and symmetric, then sample size 20, certainly that'll be fine. If you assume it's unimodal and symmetric, and you think about apples, and in general, I think we would say, okay, most of the apples that we see are around the same size. We don't really see too many outliers as far as really big or really tiny apples at the grocery store. So I think this one's going to be met. Okay. As far as big population, the population would be all apples, and or maybe all apples at the grocery store. And as long as there's a lot of apples there, this is probably this will also be met. Okay. Now we're going to go and calculate the p-value. So we want to ask, okay, what is the probability of getting our data or something more extreme? So what was our data? Our data, we had x bar equal to 4.5, and we had a standard deviation, I think was 0.7. Yeah, 0.7. Yep. Standard deviation 0.7 ounces. And so if the null hypothesis were true, whenever we take random samples, we would expect our samples to have means of around 5. We're getting a mean of 4.5. and we want to know, okay, what's the probability of getting 4.5 or something more unusual? And then also, because we have a not equal sign, it's going to be two-sided. So we would also go to 5.5 and to the right. So we want to know what's the probability of getting 4.5 or something more unusual, or 5.5 or something more unusual. According to the central limit theorem, we're going to say our sample means come from a normal distribution where the mean is equal to 5, and our standard error is going to be sigma over the square root of n. Or not sigma, s. We're estimating the standard error using s over the square root of n. So I'm going to have 0.7 divided by the square root, I think we said 20 apples? Yeah, square root of 20. So 0.7 divided by the square root of 20 is 0.1565. So this is what we have. Mean of 5, standard error of 0.1565. And we want to know, okay, is 4.5 unusual? So we're going to get basically a z-score, but because it's the t-distribution, we'll say t. Okay. And we're going to do 4.5 minus the mean of 5 divided by our standard error of 0.1565. So I have, in the numerator, I have negative 0.5 divided by 0.1565. I get 3.19, negative 3.19. Okay, t is equal to negative 3.19. And so the question is, how much area do I have beyond 4.15? So our p-value is going to equal basically the probability that x bar is less than 4.5, and I'm going to just kind of multiply it by 2, right? Because of this part is because the not equal sign in the alternative. So my p-value is going to be kind of double this tail area. This probability that x bar is less than 4.5 is going to be the same probability that t is less than negative 3.19. All right, so how do we find the probability that t is less than negative 3.19? Okay, well, we're going to have to use the t table. Okay, so we're going to go to the t table, and for degrees of freedom, I'm going to have n minus 1. I have 19 degrees of freedom. My sample size is 20. 20 minus 1. I'm going to use 19 degrees of freedom. Okay. All right. So let me, yeah. When you go to the t table, we'll go to 19 degrees of freedom, and we see kind of this row of numbers. 1.328, 1.729, 2.093, etc., etc., etc. So I'm going to come, so I just copied that one row. This one row, 1.328 to 3.579. I copied that right here. Okay. And we ask, okay, where does my test statistic 3.19 fit? Okay, so my test statistic is technically negative 3.19, but it's symmetric, so I can kind of ignore positive or negative signs. And so here I'm looking at 3.19, and I say, okay, where does 3.19 fit? 3.19 fits in between 2.86 and 3.579. Okay, so we're going to say it fits in between these two values. And I go to the top of the table, and I say, okay, well, therefore, my table area, my tail area is going to be between 0.001 and 0.005. The idea being, this is kind of how the t-distribution works, is that if you look at these numbers, the idea is we are kind of zooming in on part of the t-distribution table. Okay, so if I like zoom in on, let's say, the right tail of the t-distribution. T-distribution, 19 degrees of freedom. The idea being, if I were to draw a line, say at 2.861, or here, let me just draw a few lines, 2.539. Okay, if I draw a line at 2.539 and I shade everything to the right, this area to the right of 2.539 is equal to 0.010, this column heading here. If I go farther away from 0, the area to the right of 2.861 is 0.005. And if I go even farther away to 3.579, the area to the right of 3.579 is only 0.001. Okay? So as these t values get bigger and bigger, the area to the right, or this right tail probability, gets smaller and smaller and smaller. That's what this table is saying. So our number that we're getting is 3.19. Right? We have 3.19, and so we say, well, how much to the right? How much to the right of 3.19? Okay? And the answer is, well, I can't give you an exact value. Okay? So we have no exact value. Okay? But must be less than 0.005 and more than 0.001. Okay? So I'm going to say my area, whatever it is more than 0.001, but less than 0.005. Is that okay? So that's the statement that we're going to make. We're going to say whatever area we're looking for, it has to be less than 0.005. It has to be more than 0.001, even if I don't know exactly how much the area is. Okay, so with that in mind, we say my tail area is between this. My p-value is 2 times my tail area, right? So my p-value is going to be 2 times So if my area is between 0.005 and 0.001, then my p-value is going to be between less than 0.01 but more than 0.002. And that's the conclusion I get here. Okay, so if my p-value is less than 1%, what is the conclusion I'm going to end up making? Okay, well, I'll end up rejecting the null hypothesis, right? Our p-value is considered small. Our p-value is less than 5%, what's considered small, so we would reject the null hypothesis. So what we're saying is that if the average weight of apples is really 5 ounces, you know, is it possible to get a random sample where your average weight is only 4.5? Okay, it's not impossible, but it happens less than 1% of the time. Happens less than 1% of the time. So the fact that we did get this sample where the average was only 4.5 ounces tells us that the reason why I'm getting this sample where the average is 4.5 ounces isn't because I was one of the lucky 1% of people that got this random sample with really tiny apples, but rather that the actual population average is not 5 ounces, but it's some other number. Okay? It's probably some number less than 5 ounces, and that's why I'm getting a sample where the average is only 4.5 ounces. And so I come to the conclusion that the null hypothesis is wrong, that the mean of the population is not 5 ounces, but it's some other number, most likely some number smaller than 5. And that's why I'm getting an average of only 4.5 ounces. Okay, we ended up getting through these slides a lot faster than I expected, but I think that's okay. This will be it for, I guess let me talk a little bit about the final exam. So that's in 1 week from today, okay? And so on Monday of next week, I have maybe like one more thing to cover, and that's going to just be to compare two population means. Okay, so we've done kind of hypothesis testing and confidence intervals for numeric variables. We're looking at population means, one sample, and then so on Monday we'll compare 2 samples, and then we'll also spend a little bit of time doing review. Okay, I've assigned some homework. I told you there's going to be no lab this week, right? You just have kind of that reading assignment with some related questions. And so we'll end there, and let me give you your last view quiz answer. Last view quiz answer is the letter D, D as in dog. I hope this video recorded. I don't know quite what happened, but yeah, last view quiz answer is D, D as in dog. We'll wrap it up here, and I will say good luck to you all. We'll have a great weekend, and we'll see you on Monday for last bit of stuff and review. Yeah, question. Oh, Monday is Labor Day. What did I do? Did I make it? Okay, shoot, I totally forgot. Yeah, that's right. Hold on. Thank you for that reminder. I think I did say this. Now I'm like not remembering what I stated at the beginning. Okay, syllabus. What did I write in my syllabus here? Yeah. Oh, okay. So in order to cover required content, okay. Oh, I said an extra lecture will be given Friday at 9 a.m. Okay, so we'll do that. We'll stick to what I wrote in the syllabus. Sorry, thank you for that reminder. I totally forgot. So, okay. So I'll just, I'll log in on Zoom Friday morning, and then I'll deliver that content. Yeah, thank you. I forgot Monday's Labor Day. Okay, so we'll see you on Friday then, 9 a.m. It'll probably be pretty quick, just a little bit of new content and then some review. And then we'll see you for the final exam on Wednesday then. Okay, all right. Thanks, everyone. And we'll see you later.